So, hello everyone. My name is Immanuel and this is joint work with Alon, Hongre, Sunita and Raoul. And I'm going to talk about mining subjective properties on the web. Traditionally, if you enter a web query like movies by Woody Allen, then as a result you obtain a set of documents where you can find the answer to your query. But nowadays, search engine providers try to answer queries from structured data. This means that instead of documents where you can find the answer, you get the answer directly. In case of our example query, for instance, you already would obtain a list of movies directed by Woody Allen with some additional information, and this list is generated from the Google knowledge base. For the moment, this works for objective queries. So the example query, movies by Woody Allen, is objective since there's a ground truth for each movie whether or not it was directed by Woody Allen. But for the moment it does not work for subjective queries such as cute animals or big cities. Because for instance for cute animals there's no ground truth for one animal whether it is cute or not. Now even if there is no ground truth, for many animals there would be a strong dominant opinion about whether they are considered cute or not. And if users ask queries like this one, then they probably have some specific expectations about what should be in the result set. And queries such as those here, they are actually quite common in the query stream. And in principle, we could answer those queries from structured data as well. We could, for instance, generate a list of cute animals with some pictures and additional information. The problem why we currently cannot do this is because we need a knowledge base that captures subjective knowledge in order to answer those queries. This knowledge base should, for instance, store which animals are considered cute. So, in general, this subjective knowledge base would map entity property pairs to Boolean values depending on whether or not the property applies to the entity according to the dominant opinion. And then it would store facts like kittens are usually considered cute, why spiders are not considered cute, why New York is considered a big city, and so on. And subjective property mining is about creating this knowledge base with subjective knowledge. In principle, of course, we could create this knowledge base by hand, but we envision a knowledge base that contains information about many billion entity property combinations. And this, of course, manual creation does not scale to that. And this is why we propose to mine subjective properties from the web instead. So on the web, we are searching for statements where users have posted that they find kittens cute, for instance, or not, and then we exploit that in order to learn something about subjective properties and which entities they apply to.
And then if you really define it, like baby tigers are cute, big tigers are not cute. Some kittens are cute, some kittens are not cute.
Well, there is of course the possibility to consider subtypes of entities, but I mean in principle you could apply the same methods as I'm going to present here in order to learn something about the subtype. I mean if a user enters a query, baby, cute, I mean, that is true, sure. And we might find that out using the approach that I'm going to present. So there is already some work on mining objective properties or common sense properties from the web, but we claim that subjective properties have some particular properties. First of all, there is already no ground truth, as we have heard, so we cannot extract that ground truth from a few trusted web sources. Instead of that, we need to aggregate the dominant opinion over many different websites. Also, subjective properties are often very controversial, so we need to clearly distinguish statements claiming that a property applies to an entity from statements claiming that a property does not apply to an entity. And as we will see a little bit later, it is actually very challenging to infer the dominant opinion from the aggregated statements that we collect on the web. And for all those reasons, as we will also show in the experiments, approaches for mining objective properties work quite poorly for mining subjective properties. We need specialized systems to mine subjective properties, and we present such a system that we call the Surveyor system, because what we are doing It is a little bit like a survey because we are aggregating opinions from many people. In contrast to a typical survey, however, we do not specifically ask people about their opinions, but we collect simply what they have already written on the web and try to infer something from it. The Surveyor system has two input data sets. First of all, we have a list of entities together with an entity type about which we want to learn something. And then we have a large free text corpus, what people have posted on the web, and we try to find statements in that corpus that link subjective properties to the entities from the entity list. And in the first place, we extract those statements and we aggregate statements that refer to the same entity and to the same property. I will give you a high-level overview of how this extraction works. You can find more details in the paper. So, first of all, Surveyor uses input text that has already been pre-processed in two steps. First of all, the raw text has been transformed into a dependency tree representation using natural language processing tools. And then second, we have already identified mentions of those knowledge-based entities within the free text using diverse means of disambiguation. Then in the first step, we detect patterns in the dependency tree that hint at statements which associate a property to an entity. Then we check whether those statements associate the entity to an intrinsic property. For instance, if someone writes, Melbourne is not big compared to New York, then he's talking about Melbourne in a very specific context, and this is less interesting for our application scenario. So we want to filter out those non-intrinsic statements. And in the final step, we distinguish prose statements claiming that the property applies to an entity from contra statements claiming that the property does not apply to the entity. And the result of extraction aggregation, this is for each entity property pair, a count of prose statements and a count of contra statements. And now it actually looks a little bit like we're already done. For instance, for kittens and cute, we find 1,000 prose statements, we found 120 contra statements. So we could just say, okay, let's take the majority vote and say kittens are cute according to the majority opinion. This is intuitive, but it works surprisingly bad in practice. And we are going to see a couple of examples why it works so badly. For instance, let's say we want to infer whether one specific city is considered big or not, and we find 10 prose statements and 6 contra statements. Now we would intuitively say, oh, okay, this city is probably big, but typically with those counter values we would find that it's actually a very small city. And if we ask like 100 people about whether they find the city big or not, then 100 of them say, no, it's not big. So the problem with that is that there is skew. Because people who think that a specific city is big, they are more likely to express that opinion on the web than other people who find the same city not big. And this means that people who find a city big will always be overrepresented in our statement samples. In order to reliably infer the dominant opinion, we must take into account this kind of skew.
People talk about the big cities in Australia, but they aren't big, they're just big in Australia.
That is true. But in those cases, you could make a distinction. You could, for instance, divide the input corpus and separately consider websites from Australia. Then you would get a more fine-grained picture of what Australians think about the cities. Otherwise, if you consider the entire web, then you would get a picture of what all people in average think. Right? And of course, as I will also detail a bit later, there might be properties and entity type combinations where in general there's so much disagreement that you do not want to use them. But this is not always the case. Let's take another example. Let's say we want to find out whether one city is big or not and we don't find any single mention of that city on the web. In those cases, we can actually infer with high confidence that the city is not big. Because for cities, there's a strong correlation between whether the city is considered big and how often it is mentioned on the web. So we can exploit this type of correlations in order to make inference. However, we must be careful. Let's say we want to find out whether one animal is cute or not and we don't find any mention of that animal. In this case, we can probably not infer anything, since for animals the correlation between the number of occurrences and whether they're cute or not is not that strong. And this means, in general, that skew and correlations are property and type specific. And we cope with that challenge as follows. After the extraction phase, Surveyor learns type and property-specific probabilistic models of user behavior that will help us to correctly interpret those statements. So we learn one model for cute animals and a different model for big cities, and then we use those models in order to interpret the statement counts about single entities that we have encountered. And now I'm going to give you a little impression why it is useful to have this probabilistic model. We are comparing the output of the probabilistic model against the output of the majority vote on 500 Californian cities for which we want to find out whether they are big or not. And we would expect that to be correlated with the population count of those cities. And on the left side, you see the result from the majority vote, and it is not very correlated, and for many cities we cannot infer anything. But if we use this probabilistic model that was specifically trained for big cities, then the correlation is strong, and we can infer something for each city. I will show more experimental results later, and you will find more such examples in the paper. Our probabilistic model is a Bayes network that has the following variables. For each property entity pair, there is a dominant opinion about whether the property applies to the entity or not. This dominant opinion influences the personal opinion of each single user. We are treating subjective properties, which means that single users might disagree with the dominant opinion, but still the probability that they agree is higher than the probability that they don't agree. And the opinion of each user has an impact on how likely that user is to express his opinion on the web. And the statement counts that we find in the end, they are the results of each user's individual decision to either make a statement on the web or not. We use that model as follows. What we have given from the extraction is the statement counts about specific entities and properties. And we want to infer the dominant opinion. This is challenging, since that model includes many parameters whose values we do not know a priori. For instance, we don't know how likely it is that the user will agree with the dominant opinion. Also, we don't know, given that a user thinks that a property applies to an entity, how likely is that user to express his opinion on the web, and so on. So, in total, we have unknown parameter values, and we have random variables that we cannot directly observe. However, if we had the right parameter values, then we could easily calculate the most likely values for the random variables, like the dominant opinion. And on the other side, if we had the right variable values, then we could calculate the most likely parameter values. So there's some cyclic dependency that calls for an iterative algorithm. And this is what we use. We use an iterative expectation maximization approach in which we learn the right parameter values and the right variable values at the same time. And this approach is actually quite efficient, since we were able to derive closed form formulas for the expectation and for the maximization step. Now, we applied the system to a 40 terabyte web snapshot containing free text. It took around 2 hours to process the entire web snapshot on up to 5,000 nodes, and we inferred dominant opinions for over 4 billion entity property pairs. We have evaluated the quality of that output in several test series, and I'm only going to discuss a small extract here. You can find more in the paper. However, the results that I discuss here are representative for what we have seen in general. In this test series that I'm going to present here, we selected 500 entity property pairs. Those were our test cases. And for each test case, we asked 20 Amazon Mechanical Turk workers about their opinion, and then we took the majority opinion about the test case. And we compare Surveyor against 3 baselines in terms of the coverage. So, meaning for how many knowledge-based entities can we infer something with high confidence, and in terms of the precision, meaning for which ratio of test cases was the solution correct. We compare Surveyor against 2 naive baselines, majority vote and scaled majority vote, which do not use probabilistic models, and we compare against the WebChild system, which is a state-of-the-art system for mining common sense properties from the web that is, however, not targeted at subjective properties. And the results show clearly that our approach performs significantly better than all the baselines in terms of precision and recall at the same time. So the gap to the baselines shows that it is useful to train those specific probabilistic models, and the gap to Repchild shows that it is actually useful to develop specialized systems for mining subjective properties. And if you look at those test cases, here 2 examples, we see that there's actually quite a difference in terms of how high the agreement between different workers is. So like everyone agrees that ponies are cute, but people are not so sure whether monkeys are cute, for instance. And now we re-evaluate all the systems, and we take only test cases where the agreement between workers is very high, because those are typically the test cases which are more critical. And in that case, the performance of Surveyor even increases significantly, precision from 77% to 85%, while the relative gap to the other baselines increases even more. In summary, we have introduced the subjective property mining problem, and we have provided evidence that you need specialized systems to mine subjective properties. And we have presented our first approach for mining subjective properties, which is the Surveyor system. Thank you very much for your attention.
So something that concerns me is scaling. I mean, there's a gazillion possibilities. Small garden tools, funny looking cakes. I mean, you'll never do tests on all those. And if you're going to do something like Google, where people can type in any old adjective, noun, pair, you're never going to test them all. You're going to test a very, very tiny fraction. So how do you deal with a scaling issue?
So with the scaling issue, we consider a subset of subjective properties, of course. So we are currently considering adjectives with associated adverbs. And we are not specifying those in advance, actually, but we are directly extracting them from the web. So we infer something about properties that people actually mention often on the web, right? Because we implicitly assume that those are the properties that will also often occur in queries. So it is true that we cannot treat any possible combination of subjective properties, but I think the way we do it, we treat the most relevant ones, hopefully.
For subjective properties, it appears to me that the context in which a user asks a question would go a long way in actually determining what he considers to be the interpretation of subjective property. I wonder if you've explored that aspect of it at all.
Well, there are certainly possibilities to integrate the context of a user to make more reliable reasoning. I mean, already one simple way of doing that would be you could try to infer from which geographical location the user is. And referring to the question from before, I already said that there is the possibility to kind of create subjective knowledge bases that are specific to geographic regions. And of course, if you could like map users to their corresponding geographic knowledge base, then you would have even more reliable results. So sure, you could definitely integrate the context of the user. But yeah, apart from that, I mean, the main application scenario is like web queries that we receive, and at least in the query, usually users, they do not specify so much context, right?
One more quick thing, so I guess, in the context of your analysis for basically the where you get the evidence from, right?
Right.
Do you consider what the source was? Like basically, is it Pinterest from which the data is coming in, or is it like the open web, or is it different source? Because it appeared to me that cute animals are something which you discuss a lot in YouTube, for example. So that should be input into your system. It appeared to me.
Okay, that is true. So we basically used a big snapshot that covers basically all the text that you would find on the web. So I would assume that the YouTube comments are actually included.
No, but differentiating between that would make a lot of sense in kind of interpreting what the interpretation of subjectivity is.
So you're proposing to work only with a subset of the input data where it is more likely to find subjective
differentiate people are critical in certain forums, like something like cute animals is kind of, if I just go to YouTube and type cute animals, there will be a very large amount of hits that I'll get. So you cannot understand which animals are cute and which are not cute, just for the fact it's YouTube.
Okay, I'm not sure if I understand the question correctly, actually.
We can follow it up offline.
Okay.
Last question. Very interesting idea. A couple of quick questions. How big is the entity knowledge base? How many facts do you need to get the truth values for?
We're asking what is the knowledge base? What is the entity knowledge base?
Yeah. How many facts do you need to get the truth values for? Like how big is it? Millions? Hundreds of millions?
So the entity knowledge base only contains entities together with the entity type, right?
Right.
So the only facts that we have in that knowledge base, or the only facts that we use from that knowledge base, is basically the entity type. And are you asking how many entities of a type
Yes.
I need in order to make reliable inference? Okay, so we did not explore where the threshold is in a very principled manner, but we have some threshold of, I think, it is actually about 1,000 entities.
Oh, no, my question was how many concepts are there that you need to get the subjective value for? Like, you have cities, and then you have like animals. And for these, you need these subjective interpretations, like, is this big, is the animal cute? Like that, how many facts are there that you need to get?
Okay, so we do not specify the properties and the entity types in advance, but we search on the web which are entity types and properties that people comment on frequently.
And how many are there of those?
So in the end, we work with around 400,000 entity property combinations.
400,000.
Yes.
Okay. Couldn't you just crowdsource the values for the opinions? For Google, it should be peanuts, right?
But I mean, this is like the entity type property combinations. Like the entity property pairs, this is over 4 billion.
4 billion.
Yes. So if you ask 20 Amazon Mechanical Turk workers about 4 billion entity property combinations, I think it's going to be a significant budget for Google.
Maybe prune those. You don't need like cute cities. Okay,
you
can take that offline.
The combinations I'm talking about are only those combinations that actually make sense.
Okay.
So those over 4 billion entity property combinations are the ones where we found enough evidence to make inference. So something like cute city would not be in those 4 billion.
Okay, a final
so
question is,
prune too much.
I just googled good politician, and Google actually displayed some images with Ronald Reagan and Hillary Clinton and Narendra Modi and Barack Obama. And this points to a fundamental issue about concepts where the global truth, like assume you know the global truth, is split right down the middle. 50% of Americans believe Obama is the second coming, and 50% believe he's the devil incarnate. Now, their subjectivity itself is questionable. So the context and the personalization issue becomes important, because if you show both these guys side by side, you're going to get brickbat from the left and from the right. Yes. So have you looked into that issue?
Yes, well, I mean, I would say that there is some sweet spot of subjectivity that we should address. So if something is completely subjective, that as you say, you have basically a 50-50 random probability distribution, then it would not be very useful in order to interpret queries, right? Because it doesn't give you a lot of information.
Right.
Our probabilistic model actually already contains some parameters like the probability that users agree with the dominant opinion, and you could use those parameters in order to filter to type property combinations that appear useful in order to answer queries.
So you can use the entropy.
Yeah.
Okay.
Yes, and the probability of agreement. If you have a high probability that the user agrees with the dominant opinion, then it's probably more useful. If you have a 100% probability, then however it's an objective property.
Thank you.